So welcome everyone to the session. Got batteries, key concepts for deploying NEC-compliant emergency power. We're going to be talking today about the isolation requirements for using inverter-based sources as standby power sources, and some of the dynamics that go into it, both architecturally and from a codes and standards point of view. Next slide, please. So we're going to talk a little bit about the National Electric Code updates that are around this space. From there, that's going to lead us into talking about some of the UL standards that impact these types of solutions out there. And we're going to bring it all together by covering some core architectures and going over some online diagrams from real-world examples of how you can be using things like battery energy storage and other inverter-based sources for standby power, and how isolation needs to fit into those overall architectures, and what available content there is for you guys to pick up on there at any point on the web. If you have any questions in the meantime, you can drop them in the chat. We'll try to respond as we go. And if we can't, we'll try to follow up afterwards with any unanswered questions with a communication after the webinar is over. Next slide, please. So the first thing to talk about is codes and standards, as I mentioned. Now, the thing about codes and standards is one thing you can count on is that they're always changing and they're always evolving to keep up, and specifically to keep up with technology and to keep up with market trends that we're seeing out there. Battery energy storage, inverter-based sources, solar. It feels like we've been talking about it for a long time as a society, but it really is relatively new. And that technology is changing at a rapid rate, as well as the cost of that technology. Battery energy storage, the energy density is going up as the cost is going down. And really, as the technology matures and people start to get more comfortable with it and more confidence in its applications and its robustness, people are starting to use it more and more, especially for critical applications like emergency standby power. Some of the changes that we're seeing is the number of sources we have in systems. Traditionally, in the past, you might have seen one, maybe two sources, usually a utility and a generator, but now we're starting to see a lot more sources out there. Like I mentioned, battery energy storage. There could be solar. There could be more exotic things like hydrogen fuel cell or wind in a facility. And along with that means that a lot of these inverter-based sources are producing power that is AC, but it's really coming from a DC backbone, right? Solar and batteries, it's all coming out in DC before it hits the inverter. And with that, some of the sequence of operations and the way you design these systems has to change to account for the dynamics that brings into the picture. Not only that, but some of these sources that we're seeing are resulting in energy flow potentially being bidirectional. In the past, it used to be very top-down, hierarchical kind of way the power flowed from the top where your source was down towards your loads through your distribution. But as we're starting to see solar that could be on a panel, or battery energy storage, which sometimes it could be a source when it's producing power, other times it can be a load when it's charging. That's causing power to flow in both directions now in our electrical system, which is further changing dynamics of these systems and things that are going on out there. In some cases, people could even be back selling to utility all the way where your whole site is a source to the utility rather than a load to the utility. And that's something that has to be taken into account. And lastly is that in the past, while a lot of the codes and standards for emergency standby power were purely focused on resiliency, because that's really what you used that equipment for. So if you think about generators that were really not running 99% of the time, right? In most standard applications, ignoring edge cases like peak shaving and stuff like that. Now these types of systems like solar, like battery energy storage, people are wanting to run them actually all day, every day, not for emergency standby power, but for other applications like energy cost optimization, to save power by displacing your utility energy costs by either using your solar power, or maybe even playing kind of the stock market with a battery system where you're charging your batteries when the power is cheap and discharging them when the power is expensive, so that you save that differential in cost. So all these dynamics are really changing the infrastructure in our facilities, changing the technologies that we see being implemented in the facilities in terms of the inverter, battery storage instead of generators and things like that. And it's requiring the codes and standards to evolve with them to make sure that they are being built, designed, and applied in safe and robust ways that matches up with the technology. So one thing we've been seeing a lot of is those codes and standards evolving to keep up with all those dynamics. Next slide. So one area where we've definitely seen some of those evolutions is around National Electric Code. And that's going to be a big focus of these conversations. So I'm not going to call out the explicit article, each one, because most of the article 700, 701, 702s all have similar wording, but you'll see on the slides as you look at them that the references are there. But I'll cover some of the dynamics we're seeing across the 700 family backup power codes overall. So the first thing is that they're actually allowing sources like emergency storage systems and storage batteries, as you can see on the left-hand side here, for backup power. Article 700.12 calls that out. And that's really something that's kind of new. In the past, it was kind of a gray area, either not mentioned at all, depending on the part of code you were looking at, or explicitly forbidden to use these kinds of systems as emergency standby power sources, primarily due to the reliance and maturity of those technologies. And as that's improved and people started to desire to use them more for these applications, it reached a point where people trusted it enough, and it has now entered the code in the latest issues of the National Electric Code. So you can see right there that they're now allowing energy storage systems and storage batteries to be used for those emergency applications. The other interesting thing is on the right-hand side over here, you can see right in the very top, parallel operation of emergency sources. Down one and under normal source. The emergency source shall be permitted to operate in parallel with the normal source in compliance with Part 1 and Part 2 of Article 705. So that's actually not just telling you that your standby source, it can be a emergency storage system or a battery. It's actually telling you that now it's not only a emergency power source anymore. You're allowed to actually use that power source as a source of power in parallel with your utility when everything's fine on the system, when you don't have an outage, which is 99% of the time, right? And this kind of goes back to what I mentioned earlier about the fact that people want to pull double duty out of these pieces of equipment, these systems now. They not only want to have a backup power source, but they want to have equipment there that's helping them reduce their energy costs and reduce their OPEX costs at their facility by producing power in parallel and reducing their utility energy costs overall. So you think about solar producing power in parallel, you think about battery storage, like I said, playing kind of with the prices of the energy at a point in time and whether it's charging or discharging the system. It really lets you maximize the potential of something like a battery energy storage system so that you're using it not only during an outage, but you're also using it during normal operation facility, which brings a huge value prop, and is more of the reason that we were seeing a demand for people to want to be able to leverage these systems for emergency standby power. Because if they're already buying them for energy cost optimization reasons, they said, well, I already have stored energy. Why, or I can produce my own energy. Why can't I also use that as an emergency standby source? And that's made it into the code now and allowing that. And we're seeing that more and more. Next slide, please. Over here, we got very similar wording in other aspects of the code around allowing that. On the very top, you can see parallel operation of the emergency source shall be consistent with the sources specified in 704.c and 2, which we'll get to later. But then over here, normal source, again, the emergency source shall be permitted to operate in parallel, very similar to the wording we saw on the last page. The emergency sources shall be permitted to operate in parallel where necessary equipment to establish and maintain synchronous condition is provided. So again, they're providing some rules around what you need to run in parallel, which if you think about inverters, most of those inverters have two modes of operation. If you're planning to use it for both optimization and standby power, they have a grid tie or grid interactive mode, which is providing that kind of synchronous and synchronization between the utility and the inverter. So you're getting the energy cost optimization, but then when utility fails, it has the option to run in a grid forming mode to produce backup power standalone without having to sync to another source at any point in time. And then 705 at the bottom here, interconnected microgrid systems shall be capable of operating in an interactive mode with a primary source of power. Again, it's another wording, but it's essentially saying the same thing that the last two pieces I covered are, which is it can run together with a normal source, which is run in synchronization with that source, which is what interactive mode really means, because it's interacting with the utility grid. and producing power synchronized to that. Maybe even back selling, not just subsidizing your own energy costs. So we're seeing a very obvious pattern throughout the code that various articles are now saying that you can use batteries and other inverter-based sources and systems for standby power, but you can also use them for other applications rather than just emergency standby power as well, which opens up a lot of options for people and desirability by people to use these sources more and more. Next slide, please. Now, we've laid the groundwork that the code is now allowing people to use these types of, I'll start calling them DERs now just to standardize on phrasing, which stands for a distributed energy resource, which is basically a fancy way to say inverters, solar, that kind of stuff, right? The code's not only allowing people to use DERs by standby power source, but they're saying if you are planning to use one for standby power and you're also planning to run it in a grid interactive mode most of the time when it's not being used for backup, you have to have isolation in place. So right here you can see that, actually let's start at the very bottom. Second paragraph, the system shall isolate the emergency system from all non-emergency loads when the normal electric supply is interrupted or shall meet the requirements of 700.4. Let's focus on the front half of that. What that's really saying is that if you do have a DER that you're using most of the time for energy optimization, and all of a sudden you have an outage and you want to use it for backup power, you must be able to isolate that DER, let's pretend it's a battery energy storage system, and the critical load that you want to back up. You must be able to isolate that from the rest of your electrical system and the utility. And the reason for that is to make sure that you're not backfeeding the utility, very similar to an ATS with a generator, and to make sure you're not overloading the battery energy storage, for example, because, well, if you keep it connected and utility goes down, it essentially becomes an infinite load that I can guarantee you the battery energy storage system someone has on site isn't going to be able to carry the entire utility. So they're stating that you have to have the right isolation in place. And they take it a step further. And on the top paragraph here, you can see it mentions on the third line down, I'm not going to read the whole thing, that the application must be online. Actually, let me read it. Available within the time required for the application, but not to exceed 10 seconds. So that means that if an outage does occur, and you need this isolation to do its job and isolate your inverter so it can resume operation in a grid forming mode for standby power, that all has to happen in 10 seconds. And very similar requirements exist with ATSs and generators out there, which at the end of the day, this means it has to be an automated system. If you're relying on something like Kirk-key interlocks or a manual disconnect scheme, and you're relying on a person to do this, it's not going to happen in a timely basis to meet that 10-second requirement. So you need isolation, and these means of isolations of not just the DER, but the DER and the critical loads has to happen in 10 seconds, meaning it has to be automated. Next slide, please. So over here, we actually have an example, again, a reference from the National Electric Code. So this is actually an image captured from Article 705, shows something called a microgrid interconnect device here, which is essentially the same thing as an isolation device, or as in our world, something we call source packs of the Schneider and ASCO world. And you can see the way it's positioned. On the left-hand side, you have your inverter-based sources, your DERs. And at the top, you can see the AC loads. So those AC loads are your critical loads. So if power were to fail, this microgrid interconnect device, this isolation device, would open up, isolating those DERs and your critical loads from the rest of the electrical system that's upstream that is not going to be backed up by those DERs. So upstream of this, you could be the utility, it could be other non-essential loads, other distribution panels, but you can almost think of this almost like an emergency subpanel where you have your DER going straight into it and also your critical loads coming off of it. And this is the feed to that subpanel that when the power goes out, this opens up and now that subpanel is isolated from the rest of the electrical system in your facility. Next slide, please. Now, the other interesting thing is, so we've laid out the fact that DERs are now allowed to be used as standby power sources. If you're using a grid interactive DER for energy optimization during the day when everything's good, you have to have by code the isolation in place to isolate it from the rest of the system should power fail. But they take it again one step further and basically saying that those things must be listed. So over here, if I read through a couple of the excerpts here on this list, the equipment shall be suitable for the intended use and shall be listed, designed, and installed so as to prevent inadvertent interconnection. If I go to the next one down, I'll just read the last line on there. The interactive function and have a field label applied or both. And then the one below that, specifically 705.2 on that last one, be evaluated for the application and have a field label applied or be listed for the application. So what they're saying is these devices have to be built for this specific application. They have to be designed for this application, and they have to be listed and labeled for this application. In our world, most of the time when people say listing, the biggest agency around that is UL. What's the UL standard that this has been designed to and built in accordance with, to make sure that it meets the right performance levels, the right requirements for this application. You can't just take other products that maybe you can jerry rig them to do the job, right? But aren't purpose built or designed for this application. That's not really going to have the highest level of quality if you're jerry rigging it into the application, right? So you got to make sure it's a product that was designed specifically for this, and that it has the proper UL listing for this application. Next slide. Now the question is, if it needs to be listed, we always think UL when we think listing and labeling. What standard exactly do these types of solutions get listed against? Well, that's going to be UL 3008, which is specifically a standard for automatic interconnect switches for use in emergency systems. So this is actually a brand new provisional standard. And the reason I say provisional is because the process of creating a new standard with UL has a couple steps to it. The first step is what they call an outline of investigation, which is what I'm calling a provisional standard, using those terms interchangeably, which is the precursor to a full standard. So that was put together by a couple of subject matter experts and UL together on this topic. In this case, it's interconnect switching. And that gets published out there, and now it's treated just like a full-blown standard. You can test against it, qualify to it, list and label your product to it. AHJs would consider that listing and labeling the same way they would a full-blown standard. The only difference is that before it goes to be a full-blown standard, it goes through one more review cycle together with a larger committee of other industry experts in that space, other manufacturers, specifiers, contractors, anyone who has subject matter expertise. They basically just open up that committee, that group, to more people to take the provisional standard, which is basically like a first draft, go through it, revise it, edit it. And once the entire community of subject matter experts, not just UL, not just one company, but the entire community, including many competitors in some cases, are in agreement, it gets voted into being a full-blown standard, like any other standard you're used to seeing out there. So for all intents and purposes, treat it as a standard, but just know that there are still opportunities to edit it and revise it before it gets promoted to that full piece. But as it exists today, UL 3008 is, as I mentioned, around interconnect switches for emergency power. And it really takes two standards and kind of puts them together with a little extra special sauce. It takes UL 1008, which is the ATS UL standard, the transfer switch standard, which is obviously focused around standby power applications. And it takes UL 49, which is the circuit breaker standard out there, and takes kind of both parts of the best of both of those and puts them together. And what I mean by that is that ATSs clearly have a standby power application. Since these devices don't have to switch between two live power sources, it's just about isolation. It really works more like a breaker. But if you look at the bottom here, we have a list of some of the tests that go into UL 3008. Some of the tests you're going to see are things that are familiar to both breakers and ATSs, things like endurance testing, how many cycles can it operate, overload testing, temperature rise testing, short circuit testing. But the thing is, there is a difference between UL 49 and UL 1008 on how they do those tests. And that difference is that UL 489 allows each of those tests to be done independently with a separate sample, a separate circuit breaker. So every time you're going into a new set of tests, whether it's endurance, temporize, overload, you're going in with a pristine, perfect sample because it's a brand new breaker every time. UL 1008 for transfer switches actually requires that most of those tests be done on the same exact sample. So that means as you go into each test, it gets harder and harder to pass because the equipment has already taken all the wear and tear from the previous test it did. So at the end of the day, UL 1008 qualification for electrical performance is much more difficult to pass than a circuit breaker UL 489 because you have to pass all those tests on the same device, basically, instead of using a brand new device for each test independently. And what that means is that although you can use a device like a circuit breaker to provide isolation conceptually, to use one that is UL listed for this application for 3008, you can't just take any circuit breaker. You have to take a circuit breaker and put it through the more robust UL 3008 test sequence to make sure that it meets the UL requirements for automatic interconnect switching, which is similar to the UL 1008 standard. So you can't just take any breaker off the shelf and put it in. Will it work from a sequence? If you have the right controls, yeah, maybe. But unless it's been tested to 3008, you can't guarantee its electrical performance for this application. And there are differences in the way breakers and ATSs are manufactured to handle that. So we can tell you right now, not every single circuit breaker out there is capable of passing a UL 3008 qualification for standby power as laid out in UL 3008. So you got to make sure if you're doing that, you're looking at 3008 listed equipment. Another interesting piece is that all these tests actually have to happen ×2. So this is a part where it improved beyond the ATS standard, where it only requires testing of current flow in one direction, because traditionally in the past, current usually only flowed in one direction. Well, now, as I mentioned, things are bidirectional. Sources can become loads and vice versa. And things can be feeding in either direction on the same circuit. Every single test actually has to be done twice, once with current in the forward direction and again with current in the reverse direction to ensure the equipment can handle that in both cases. So that's another dynamic that's different in UL 3008 than other standards that you might be familiar with. Some other tests that go into are electromagnetic compliance, over and under voltage operation. Those are pretty standard tests. But of course, there are some very sequence specific things. So again, you might be able to use an ATS or a circuit breaker, you think, for these applications, but the sequence of operations for interconnect switching and isolation switching is different than that of a circuit breaker for overcurrent trip, or a ATS that's trying to switch between two sources that are always isolated from each other, right? In this case, you actually want the inverter to be in parallel with utility when everything's okay and only isolate otherwise. Now, that means you have different sequence of operations you need, and as a result, the testing is different because of that for this standard relative to 1008 or 489. So if I summarize the last couple of slides, the National Electric Code is now allowing distributed energy resources like battery energy storage to be used as a standby power source. They are mandating that when you are using it in grid interactive mode, which of course you'd want to do that to save money when your utility is okay, you have to have the right isolation means in place to isolate it and your critical loads from the rest of the system before it can turn on in standby power mode, in grid forming mode, basically. And that device that provides the isolation to the system has to be designed, tested and labeled for the specific application of emergency standby power and isolation and interconnect switching, which is where UL 3008 comes to play. Now, all those things come together, and one of the first devices out there, next slide, please, is the ASCO source pack device, which is an interconnect switch device designed specifically for those applications, listed to UL 3008 to meet those National Electric Code requirements and the market's needs and desires. And to take it from here, I'm going to hand it over to my colleague, Benny.
Yeah, thanks, Victor. So Victor gave a lot of good context there on the National Electric Code and our UL 3008 listing and how it's designed and tested specifically for not automatic isolation, but also automatic reconnection to the primary service. And with that, we have source back here, which you see there in the bottom left. And we like to use the analogy what an ATS, automatic transfer switch, is to a generator. source pack is to a battery energy storage / inverter based resource. How this differentiates than most microgrid solutions when you're thinking about designing for resiliency. At some level, most microgrid systems require some type of microgrid controller. That could be a very basic level microgrid controller. We have IO contacts that communicate to an energy management system, or you have sophisticated microgrid PLC controller that's activating several use cases in the energy storage system. But today, for most applications, I would say for commercial industrial segments where you incorporate a photovoltaic battery energy storage system and want to use that energy storage system for resiliency, SourcePack is a product that's specifically designed, as we mentioned in the UF 2008 listing, that's designed to specifically isolate, communicate to a battery energy storage system to enable resiliency. We specifically isolate those essential loads, and whatever energy storage that panel board that's connected to the energy storage system will provide power to those circuits in that panel board. And the most important thing to think about this is energy storage systems. Yes, you're getting the energy optimization benefits where you're saving money during the day when it's grid connected. But you also want to enable the resiliency, right? You want to maximize the full potential of your battery energy storage system. And SourcePack is one way to do that, and a simplified process to enable battery resiliency. So how SourcePack works, SourcePack has a controller, and that controller monitors voltage and frequency. It has a motorized breaker. When SourcePack detects that the utility feed is no longer available, it will isolate or open that motorized breaker and essentially isolate a portion of the electric facility, that panel board where your energy storage and critical loads are connected to. And it will send a signal to that battery inverter system through a C-form contact, much like a transfer switch, telling it, hey, we're safely isolated. Now you can enter a resilient stage where you can create your own voltage and frequency, provide power to those critical loads. And of course, when utility returns, SourcePack remains isolated. So the controller will sense that a utility is returned. Now there's a time delay of when you can reconnect back to utility, but it remains isolated and will send a signal to the inverters, telling them to shut down. You obviously don't want to close that breaker when utilities online and back feed. So we'll send a signal to the inverters, telling them the utilities return, shut down that breaker, reclose, energize that critical panel board, and your inverters will operate again in a grid type operation. So these are some core architectures. When dealing in microgrid design, it's common to see energy storage or photovoltaic systems. And primarily they're connected on the utility switchboard, which for most applications that's ideal. But if you want to specifically use these energy storage systems for resiliency, at times it's important to design them with critical panel board in mind. So when you lose power during that 1% time of the year, that you can maximize your ROI or the resilience in the battery storage system, provide backup power to the essential loads, not the entire utility main switchboard that is feeding. There's also architectures where the generator and energy storage system coexist. And what I mean by that is energy generators are legally required for life safety and legally required loads. So an ATS is there to provide power during those extended outages, think fire pumps, elevators, places like that. And then also you have SourcePack or energy storage system providing power to other essential loads in your facility. They could be optional standby, where both ATS and SourcePack operate independently, but they still provide resiliency to their respective loads. And then we go to the far right there, which is a battery first scenario where, again, if you think about your battery energy storage system connected to utility main switchboard, which ideally is where you want to connect an energy storage system because it's a grid connected device. When you lose power, these inverters can change state almost instantaneously. We're dealing with electronics here. So when you lose power, you could isolate, or SourcePack will isolate from the utility main. That inverter can change state almost instantaneously, grid tied to grid forming, energizing that utility main switchboard. Where downstream you have these ATSs, they will stay connected to source one. So this is almost like a battery first scenario where you lose power, your energy storage system comes online first. So those ATSs will detect a momentary outage, stay connected to source one. If for whatever reason that battery energy storage system hits a low reserve, then the ATSs will detect there's been a true failure. It will switch from source one to source two, basically allowing that generator to act as the secondary emergency power source. So we're going to go over a couple architectures to highlight how SourcePack is utilized. As Victor mentioned, SourcePack is designed to be installed downstream of your utility switchboard. And what we mean by that is you want to isolate those essential loads where your energy storage system is connected to. These are the loads that when you lose power, you can disconnect from the utility, and you want your energy storage system to provide power to these essential loads. Battery energy storage systems, depending on the chemistry, technology, most of them are sized for a minimum of 2 hours of runtime. You can get 3, 4, 5 hours, and some chemistry can get a longer duration storage systems. But essentially, they have a finite amount of power that in the event of a prolonged outage, you want to make sure you're powering the essential loads, not the entire facility where most loads are not essential. So if we go through this animation here, this is from the signal line diagram that we worked with with a consultant. And here you have an incoming utility. This utility is feeding into your board. Now on the far right there, you see SourcePack highlighted there. It's designation DS ISO. And then upstream of SourcePack is this critical switchboard or panel board where you have your energy storage system and your solar system connected to the switchboard. And then feeding off of those two breakers, you have essential loads, which are yet to be determined here, but these are the loads that maybe office lighting or you have specific panel board you want to provide backup power to. So during grid tight operation, you're getting the energy optimization from your battery energy storage system. Any excess power is getting exported back to the utility main switchboard. But more importantly, when you lose power, you're also enabling resiliency out of that battery energy storage system. So when you lose power, the utility main switchboard will go dark. This is as common. Those inverters in the solar and battery energy storage system shut down. They're dependent on an anchor resource, and when they lose power, they shut down to prevent any backfeed to protect utility workers upstream. Now, when SourcePack detects this outage, the controller will sense it. It will isolate the motorized breaker. SourcePack will send a contact signal to the inverters of the battery energy storage system, informing them that we're safely disconnected from the primary service. You can perform islandable condition, change from grid tied to grid forming. That battery energy storage system will come online, energize that switchboard. At the same time, the solar system, which is dependent on an anchor resource, will come online as well. And now you're providing backup power to those essential loads in a very simplified fashion without a complex microgrid controller to do so. Now, when utilities restored, SourcePack will remain isolated. Now, there's a time delay up to 60 minutes that can inhibit reconnection to utility. SourcePack will sense that utility is restored. It will send a contact signal to the battery energy storage system, telling them to shut down. Those inverters will now shut down. You will lose your solar system at the same time. Those loads and the switchboard will go dark. At this point, SourcePack can now reclose its breaker, and then the switchboard will be reconnected to utility. And now you're again operating in a grid tight operation where your solar and battery storage system are providing power to the essential loads, and any excess is being sent back to the main switchboard or utility if you have a power purchase agreement. Now, this other animation we're going to go over is for battery and generator. And again, this is the use case I talked about, one of the core architectures, but you still have a generator there. And again, when it comes to reliability in a microgrid, it's hard to replace a genset. And what we mean by that is for those prolonged outages, anything longer than 3 to 4 hours, you need to have to rely on emergency power source to ride through those extended outages. Not only for that, but also for code requirements. You maybe want to have your life safety legal requirement of a generator, or in the event that you lose power and your energy storage systems hit a low reserve, you can use the battery energy storage system to provide to charge those batteries. So in this in this architecture here, we both have ATS and source pack, where they both operate independently. What we mean by that is the utility's lost, the ATS will transfer those critical loads to generator, and source pack will disconnect from the primary service, segmenting those essential loads to allow that battery energy storage system to provide backup power. And this is the same animation that we went through. The only difference here is now we've added a transfer switch off the utility main switchboard, where your ATS is now providing power to the essential or life safety loads, and your source pack is still connected to utility here, where you're getting the energy optimization benefits from your energy storage system and solar system. Now, when utility fails, both ATS and source pack operate independently. The ATS will sense that utility is lost. It will send a contact signal to the generators to start. Source pack will detect utility has been lost. At the same time, again, those inverters, the energy storage system and solar system will shut down. Source pack will isolate. It will send a signal to the BESS, telling it to change state from a grid tie to grid forming. That battery energy storage system will come online first. And when it comes to re-energizing the bus, again, these inverters operate instantaneously from changing state. So if you need to go from a grid tie to grid forming, that'll happen much faster than when a generator comes online, which normally takes about 3 to 6 seconds. So at this point, you're disconnected. You're in, I guess, an operable condition where your source pack disconnected from the primary service. You're providing power to those essential loads, and your ATS is now a generator providing power to those critical, legally required loads. Now, utility returns. Again, both ATS and source pack will detect that utility is restored. Source pack will send a signal to shut down the inverters in the battery energy storage system. Inherently, once those inverters shut down, the solar system also goes dark, so everything, your switchboard is now in the dark. And again, this happens in a open transition. So when we lose power, breaker opens up, and then when we return to utility, it's a break before make transition. And then the same goes for the ATS here. Once we detect that utility return, the ATS will transfer to source 1. Source pack will close the breaker, re-energize the essential panel board or switchboard, bring in online the battery energy storage system, and your ATS will transfer over. Again, they both operate independently. For this scenario, the generator and battery energy storage system coexist. You can think about this architecture if you have an existing facility that has a generator and they want to add on renewables or battery energy storage system. Again, you can install, off the utility main switchboard, a source pack device, and then downstream have your energy storage system and battery energy storage system installed. That's a quick, convenient way to add renewables to your facility. Just different architecture to consider as we're dealing with, photovoltaics and energy storage systems and how to incorporate them in a single line design. So this next use case is battery first, and this is probably the ideally most preferred if you can design your system in this fashion. And what we mean here is within your utility main switchboard, you have your energy storage system connected to that board, and then downstream you have your automatic transfer switch with generator. What this does is when you lose power, you can isolate from the primary service. Your energy storage system can come online first, provide power to that main switchboard to your ATS and stay connected to source 1. And then when you truly lose or hit a low battery reserve in that energy storage system, your ATS will detect that power has been lost and then transfer over to the generator. It allows for a more sustainable emergency power source where you count on a cleaner energy storage system to come online. And then it gives you the redundancy as well in the generator where you're going battery first. Most outages, and they last a little bit, like an hour, 2 hours tops. But for whatever reason, that should extend beyond, the duration of the energy storage system capacity. You have the genset there for an N+1 emergency power scenario. So if you look at this single line diagram a little bit differently than what we previously discussed, you have utility downstream from the main service disconnect. You have source pack feed into a main switchboard. And then if you look there to the loads, you have two PV systems connected to the main bus. You have a battery energy storage system connected, and then 2 ATSs feeding off of that main switchboard, which are connected to a generator. Now, what's beneficial of this design is when we lose power, source pack will isolate from the utility. So it would open the motorized breaker. At the same time, as it detects utility outage, it will send a signal to the battery energy storage system telling them we're disconnected, come online. Again, this can be configured where you lose power, source pack opens its breaker within a second, and then at that same moment, the battery energy storage systems will change state to grid forming and energize that bus within probably 2 seconds. Now, at the same time, you can inhibit the start signal to the generator, or for most ATSs, they don't initiate start signal until 3 seconds after utility's lost, and that's programmable. So you can keep the ATSs on source one. In this fashion, you're running on battery storage as your emergency power source, and you're keeping the generator offline. So again, a more sustainable emergency power source than calling on the diesel genset. Now, let's just say the battery hits a low battery alarm. The outage lasts longer than 3 to 4 hours. At that point, the ATS will detect that utility's been lost. It will send a signal to the generator to start up. The ATSs will transfer that load. So those essential loads that are being from the ATSs, the ATS will transfer that load, power to those essential loads. And then when utilities restored, source pack will remain isolated. Again, the key feature here is not to reconnect instantaneously when utilities return. You want to signal to the battery energy storage system that the utilities coming back online, get ready to synchronize again and operate in a grid-tied operation. Now, source pack, close that breaker. Your main bus will be energized. The inverters and the battery energy storage system will sense that the primary service is reconnected, as well as the photovoltaic system will sense that the utility has been restored. Both photovoltaic and energy storage system will operate grid-tied operation, and then the ATSs will transfer from generator back to utility in an open transition. But again, this is the ideal scenario where you want to use the battery first, where you're calling the battery energy storage system to provide emergency power first, and you have the redundancy in the generator for those prolonged outages. And resources. So some of our core architectures I discussed, they're available in our brochure. We talk about what we see most commonly in these microgrid designs. And again, we're mostly focused on the commercial and industrial segments, where think K through 12 may tend to fit out some type of commercial building where they want to install microgrid, and they want to find a clever way to enable resiliency. We talk about some of the core architectures there. We have our data sheets available. So source pack is available in 600 amps at 480 volts, and that's common with most energy storage systems. They operate at 480 from the output transformer. So if you're designing a system, source pack will work in hand with the energy storage system. Next year, we're going to launch our 800 amp option and 208 volt option. So you'll have both voltages available, 480 and 208. We have our drawings available online. So if you want to know what contact signals we require to pull, feel free to view online and check our outline drawings and wiring schematics. And we have a lot of technical bulletins, white papers to show what's different from an ATS compared to an automatic interconnection switch. And I guess the main thing I can reemphasize is ATSs are connected, that are transferring from source one to source two. Here we're isolating a downstream load, and again, battery energy storage systems or energy storage systems are essentially loads that can become power source. How do you disconnect the load to enable a power source? You require an automatic interconnection switch, right? You would want that battery energy storage system connected to source two of your transfer switch, where it's on standby, because at that point you're not getting the energy benefits during grid-tied operation. And then we have guide specs. Again, this is the UL 2008 is a provisional listing. It's the first of its kind. So we do have guide specifications for Division 26 that we now have available to share with folks on this call. If they're interested, feel free to ping us online for more information. And if you're interested about accessing these resources, here's our webpage. You can log online or scan this QR code. ASCO, type in source pack, and we have a bunch of information there on the product. Again, a lot of blogs, technical papers to help you understand how this application is used and the use cases that we see your source pack in the microgrid application. So that's the presentation there. I hope the audience here found it insightful. And if any questions we can answer, but we can do so here.
Thank you for joining in. Appreciate it.
Yeah. Thanks again, everyone, for joining in. Hope to hear from you soon. Take care, guys.